to give you an outline, we really want to cover like chapters 10 and 11. Definitely by like April 20th, and then have like the last 10 or 12 days in April to cover any like additional small topics. So oscillations occur, Newton's law of gravity, very simply occurs. Stuff that you probably saw a little bit of last year, but stuff that we still want to talk about. The pace we're at, to be honest, I don't think we're going to have too much review time at the end of the year. So in Calc right now, how are you guys doing? Are you almost done with the year?
We're finishing.
We're still doing.
We've done all the derivatives. We have like one more integral.
Have you done volume integration yet?
Yeah.
We're like rotating a solid to create a solid.
Nice. Are we like far along?
So
I hate those.
in Calc, you'll probably, I'm gonna guess in Calc you'll have like a week or two of review in April. That's my guess on the Calc course, just based on where you guys are at now. I don't think we're gonna have much time to review here. And this is the first exam of exam week, just so you guys are aware. Yeah. So it's a double whammy, but we'll do our best. Yeah.
For physics and calculus for the like fourth quarter, are we still gonna have 2 tests?
I think you'll have 2 like half tests or 2 short tests. I'll try to give you guys one like early April, maybe 2 weeks into April, and another one, at the end of April. So or 2 weeks between each. So they won't be full.
Nothing after the AP test.
Say again?
We're like done with the
Third quarter is just next week. So
Yeah.
you guys have an exam next week on Wednesday, and then on Friday we'll start the fourth quarter material, even though it's not fourth quarter yet.
And then this information is going to be on the
10-1 through 10-4, definitely. If we get to 10-5, possibly. And that's based on today's class, Friday's class, and then you guys have the test on Wednesday. Because Tuesday is Ignition Awareness, so that's not an extra day. Yeah, we lose too many days, and with every other day this year, it kind of screwed everything up. I mean, I'm thinking like, I thought about it the other day, this would be the equivalent of like, right now where we are on last year's schedule, we'd be in the very end of the second quarter, time-wise. Like, the time that we've allotted for this course has only accumulated up to would be the end of the second quarter right now. We would still have the whole third and fourth quarter, and we're like doing really well paced if we had last year's schedule. But for this year's schedule, we're like a little bit behind, which is. We should have something different for physics, yes. Next year, I'm going to push for at least a 4th meeting time with me, not as a recitation, but an actual lecture meeting time. They should what?
They shouldn't do the schedule.
I like the every other day for some classes because it does push how colleges run, and it gives you guys a little bit of a breather between each day. But for an AP course that requires a lot of material, I think we need a 4th meeting spot, which is what bio has. So if you know about bio, they have a 4th meeting time. Yeah. So that Miss Myers requested that earlier in the year, and I didn't think to request it, think we would need it kind of thing. And now I'm thinking about it. Anyway, so let's look at chapter 10. We'll start with section 10.1. We're talking about here rotations. Okay, or rotational motion. Specifically, we're going to start looking at all of the equations that we had in the beginning, but with rotation. So we have to write a couple of things down. First, I'm going to jot down some general formulas that you should know from math. S equals theta r should be one that you know from math, where theta is in radians. This entire chapter, units of angles, will be in radians. If they're given in degrees, or if they're given in rotations, you want to convert to radians right off the bat. Okay, always in radians for this. And I'm trying to simplify everything that's in this chapter without going into a lot of detail. Displacement, angularly. I know, right? Weird word. It's theta 2 minus theta 1. Same thing as displacement linearly, except instead that was x2 minus x1, or y2 minus y1. Okay. Angular velocity. The average angular velocity is the change in the angle over the time period. Okay, omega is the symbol for that. Just give me a heads up real quick. we see this symbol last year? The rotation? Okay, I want to make sure we're all on the same page. I know we introduced it, I didn't go into a lot of detail, but enough that this should be familiar still. Now, where does the advanced portion of this come into play with angular velocity? Instead of looking at the average velocity, we can find the instantaneous angular velocity. The instantaneous angular velocity is defined as d theta dt. And again, that's the instantaneous angular velocity. What are we doing really? We're taking the limit as delta t goes to 0. We're doing the limit up here of delta t going to 0, meaning a small time period. So at an instant, what is the angular velocity of the record that's rotating on an old record player? Or the gravitron rotating, whatever it is that's rotating. If we want to figure out the angular velocity at an instant, we look at the derivative of the angular position at an instant. This is just like velocity being the derivative of displacement. The same concept, right? This is analogous to v equals dx dt. Okay.
I was going to ask when it's coming to angular velocity, is like the path around the actual, like, the circle instead of a tangential velocity? Makes sense?
Yeah, that does make sense. So Chip is talking about a point at the very outside moving. That has tangential velocity at the edge. The angular velocity is any point on the rigid body rotating. So if I were to do this, actually I'm going to choose this water bottle. If we were to spin this water bottle here, okay, the very most outer part has a larger tangential velocity than an inner part because it's physically traveling a longer distance than the inner part is. But the angular, not tangential like I said, but the angular speed or angular velocity of any point on this object is the same value. It's how many degrees it covers in a given time. So whether here's the rotating axis, whether I'm here or here, I'm covering the same degrees because I'm moving as a rigid body. The key is that all these problems involve rotations of rigid bodies, which simply means that the body itself doesn't have like two parts that are rotating at different rates. Okay, they're rotating together as a rigid body like that. Okay. Now, similarly, we have acceleration. And acceleration is given by the symbol alpha. The average acceleration is the change in the angular velocity over the time period. Just, again, like kinematics from earlier, from one dimension or from linear kinematics. Acceleration was the change in velocity over time. Now acceleration is the change in angular velocity over time, because we're looking at the angular acceleration. And then finally, if we want to find the instantaneous angular acceleration, we take d omega dt. And what would the units be there? Alpha, not radians per second. If it's acceleration now. Yeah, just like meters per second squared was. Okay? So you can group these together mentally. There's no reason to have them grouped separately, right? Because these are the same things. One is average, one is instantaneous. Up here, one is average, one is instantaneous. The formulas are the same as earlier this year with linear velocity and linear acceleration, but now it's rotational. I don't think, I should have checked before this class, I don't think you're given a lot of these equations on your formula sheet. I think you're given a couple random ones, so we should look at that together to see which of these you want to either memorize or put in your calculator or recognize the analogous nature to remember them. Let's see. Okay. So the first sample problem given in the book, I'm not going to go into crazy detail because I think it's kind of pointless actually. The first sample problem gives you a function for theta. It gives you theta as a function of time. And then it asks you for the velocity, the angular velocity at a given instant, which is the derivative, plug in that time. Then it asks you for the angular acceleration at a given moment. Second derivative, plug in that time. So the first example problem in your text is really just involving taking derivatives but using these formulas instead. So they give you some theta function as a function of time. And the problem is -1 minus 6t plus 0.25 t squared. And then it simply asks you to find the instantaneous angular velocity and instantaneous angular acceleration at given moments. So it's not more than taking the derivative. So if we want omega, we say it's d theta dt, which in this case would be -6 plus 0.5 t. And then if we want acceleration, it's d omega dt, which is just going to be 0.5. I'm just taking derivatives once and then again. Okay, I'm just taking derivatives once and then again. So that's the example that they use in the book. I don't think it's a very worthwhile example to go through all the numbers for it and do all the work, because then they ask you things like find out, let's see, graph omega as a function of time. Okay, so graphing this as a function of time looks linear. When will this object have a minimum or maximum displacement? How do you do that from your calc class? When do you find a max or a min? Or how do you find a max or a min of a curve?
You take the derivative instead of equals, correct?
Yeah, and it's the same thing here. If you want to know what the minimum or maximum position is for theta, take the derivative, which is here, -6 plus 0.5 t, set it equal to 0. The same logic that you're learning in calc applies to these laws, but here now we're just looking at new scenarios that are rotating instead of sliding or moving up and down. The next sample problem, the next one's probably a little tougher, so I can go through that one. The next sample problem is page 264. You're given the angular acceleration as a function of time. And the problem says a child spins a top, like a dreidel, a top, where the angular acceleration is given with t in seconds and alpha in radians per second squared. At time equals 0, the top has an angular velocity of 5 radians per second. What is that called in calculus? At time equals 0, the object has an angular velocity of 5 radians per second. What am I giving you, or what is the book giving you with that information? Do you remember what it's called? Good, kind of like a c value. Very good. The y-intercept, the constant. Have you called those initial conditions at all? No? Have you talked about boundary values and boundary value problems in calc? Okay. So the phrase is initial condition, but it doesn't need to be used that way. It just means the condition of this object initially, in the beginning, at time equals 0. So the condition given was at time equals 0, the angular velocity is given as 5 radians per second. And this will allow us to determine the c value. Because if I just integrate, I'm using an indefinite integral, right? And I get a plus c. So I don't know what omega as a function will look like unless I'm given some information, and that's the information there. So part 1 says determine the function omega. So omega is going to equal the integral of alpha dt. Again, omega is going to equal the integral of alpha dt. And where does that come from? That comes from the fact that earlier we said that alpha itself is equal to dw dt. This is a separable equation. Calculus yet? Separable? Have you done that? Have you heard that phrase? Separable? Separable differential equation? It may not have come up. Some of you are nodding yes, some are nodding no, so I'm really not sure actually if you did or didn't learn it. So what you do to solve an equation like this? Yes. You move the dt up you go like this, and then you integrate both sides. But what's the integral of a dw? It's just w. So this becomes this right here. This is called a separable differential equation. We actually did it, we didn't call it that earlier this year, but we did it with drag force. We said the drag force was proportional to the velocity itself, and that derivation of that comes from a separable differential equation. So you move dt up, you integrate both sides, and you're told that the angular velocity is the integral of angular acceleration. But this is nothing new to you. This is, again, analogous to linear velocity. The linear velocity is the integral of normal linear acceleration. And that is back in calculus. You guys have learned that already. Your position becomes velocity, which becomes acceleration when you differentiate. So when you integrate, it goes back in the other direction. So if w, or omega rather, is equal to the integral of alpha, let's go ahead and do it. And this problem allows us to recognize that omega is going to be 5t to the fourth over 4 minus 4t squared over 2 plus c. I know the 4 over 2 reduces. I'm just doing it one step at a time, so in case people are confused. And now we need to figure out what c is based on our condition given. So we take this condition that's given right here and apply it to figure out what c is. So what's c? 5. And that's convenient because these are not trig functions. Notice here, don't fall into the case where you think c is always going to be whatever this number is. It's not always going to work out that way. If this were cosine of t, well, the cosine of 0 is 1. So when you plug in a 0, it'll zero this out, it'll zero this out, and that's great. But if it's cosine or sine or something else, it doesn't always work that way. So you still have to apply the condition. So the condition says when omega is 5, t is 0. And again, if it's a simple one like this, you should definitely just do it in your head. This is 0, this is 0. So as a result, c is equal to 5. Okay, again, I'm applying this condition right here into this equation. I can use a red line to show you that. I'm taking this condition right here and applying it into that equation right there. That allows me to solve for c. And as Chris said, c is 5. Okay, c is indeed 5. So my omega function now is whatever I had a moment ago with a 5 at the end. I will simplify things to make it look nicer. And there's my omega function. So I've used a condition to help you to figure out the generic solution to the omega function. The condition is that at time equals 0, the angular velocity is 5 radians per second. Can you expect or can you predict what's going to happen next or what the next part would be based on a scenario like this? What else could you be asked to do?
Find the indefinite integral
Of the position. Very good. So the angular position would become the next part from this. So let's take a look at the angular position now. We know that d theta dt is equal to omega. This is separable, so let's separate it. D theta equals omega dt. Integrate both sides. Theta is the integral of omega dt. So just as Chip had predicted there, if we integrated acceleration angularly to get velocity angularly, we're now integrating our angular velocity to get our angular position. Just like we do from A to V to X. The same thing as what you're doing in calculus right now, but instead of this being X and this being V, now this is theta and omega. Just representing that it's angular, not linear. The other condition I think was given also, we're told that at time equals 0, it's at a position of 2 radians. That's our initial condition. We can now integrate this. Theta is going to be the integral of this entire function. It was 5t to the 4th over 4 minus 2t squared plus 5 dt. That integral is just power rule, pretty simple integration. This will be 5t to the 5th over 20, which can definitely simplify, minus 2t to the 3rd over 3 plus 5t plus a constant. Okay, again, I'm integrating each of these separately, 1, 2, 3, tacking on the constant. Again, how do I find my constant? By applying the condition in red. By plugging in a 0 for t and a 2 radian for theta. Okay, and this is how you should be seeing the problem. Because there's no trig functions, and there's no function where we're evaluating a 0 besides a linear, quadratic, cubic, quintic, whatever here, and polynomial, these are all going to become 0. So C is simply 2. Okay, C is going to be 2 for this problem. So what does that make our final answer for theta? That makes our theta function equal to, let's see, 5t to the 5th over 20 is just going to be 4t to the 5th minus 2/3 t cubed plus 5t plus 2. Again, just stepping you through the process so that you see the analogous nature to linear stuff.
1/4?
Thank you. 1/4. Thanks, Sam. The first should be 1/4. Okay? Should be a 1/4 right here. So far, so good? Integration derivatives, right? Integration derivatives. That's section 10.1. Let's go to 10.2. So 10.2 is just as similar as 10.1 is to linear quantities. We're going to take the linear equations and just write them angularly. So I'm going to jot them down on the left side in a linear fashion and on the right side with an angular fashion. So on the left side here, we had a couple from earlier this year. First, we started with V equals V naught plus AT. Second, we had X equals X0 plus V naught T plus 1/2 AT squared. And third, we had V squared equals V naught squared plus 2A delta X. Those were the big 3 that we've worked with. There are like 1 or 2 others that you can derive from those 2. Okay, and we actually talked about them, and I said to you guys, you probably want to store them in your calculator because these last 2 I'm going to write here are not on your formula sheet. Okay, this other one was the following. This was X equals X0 plus 1/2 V0 plus V times T. And the last one, X equals X0 plus VT minus 1/2 AT squared. I don't know if we actually ever went into the last one, to be honest. I know we did this one because this involved using the average velocity, half of the 2 summed together, average velocity, which is equal to the acceleration there. But I don't know if we ever ended up doing this one earlier on. So if these are new, or if you're like, I'm not sure about these, just think about putting these in your calculator as 2 additional equations. They're not on your formula sheet. Okay, but because your book transcribes them into angular equations, I'm going to just put them there so you have them.
What's between the second and last one?
Yeah, the second one involves the initial velocity. The last one involves the velocity at a given moment when there is no initial velocity. All right, let's go to angular stuff. So what would the first one look like angularly? Just transcribe all your variables at this point. What does v become? Velocity becomes, yeah, what is that symbol called again? M had it. She went like this. What's that symbol called? Omega. So this is omega equals omega naught plus alpha t. The second one, theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And then I'm going to keep going through it, right? Omega squared equals omega naught squared plus 2 alpha delta theta. Theta equals theta naught plus 1/2 omega naught plus omega times t. Theta equals theta naught plus omega t minus 1/2 alpha t squared. So you're literally replacing v with omega, x with theta, and a with alpha. Okay, and wherever you had meters in the previous spots, what do we now have? Radians. Radians. Okay, wherever we had meters for units, now they're radians. That's it. That's all you got to remember for this. Now, does this get tougher? Absolutely. But the first 3 or 4 sections of chapter 10 are the more straightforward part, where you're really just transcribing linear and taking it into angular. We'll get into more of the other stuff like F equals ma becomes a whole other equation with angular. But it is analogous. It is still analogous. Instead of F equals ma, we're going to have something else. Instead of F, it's going to be torque. Instead of torque, we're going to look at, instead of ma, it's going to be I alpha. I stands for rotational inertia. But we're going to get to that still. But I want you guys to see how these equations are very, very similar. So when there's something rotating and you're looking at the angular acceleration or the angular velocity, know to use the same equations you had here, but in the angular form. While we're sitting here, can somebody just check the formula sheet and see if any of this is on there? Take a quick look. Looks like Bridge is pulling up for us. See if any of these are on here, or even if any of the derivatives from earlier are on there at all. If you haven't saved yet. Anyone has it saved? Yeah? Let's see what we got. So we're looking on the left side here. All right, so some of them are given at the bottom. I'm going to put an asterisk on the ones that are given. This is given at the bottom of your formula sheet. Where is it? Right here. That's given. That's given right there. I think that's it. Let me just make one last look. Yeah. There are some other formulas we're going to see in a moment that are also given, but we haven't gotten to them yet. Those are the only given formulas on the formula sheet when it comes to these 5. Okay, so keep that in the back of your mind. You should know S equals theta r from earlier. I don't think that's on the formula sheet. Maybe it is actually, but S equals theta r you should know from pre-calc last year and from calc again this year. So the example problem, I'm not going to go into depth. I'm going to talk it through so you guys can get an idea of it. It says a grindstone rotates at a constant angular acceleration of alpha. It gives a value 0.35 radians per second squared. At time 0, it has an angular velocity given and a reference line on its horizontal at the angular position theta equals 0. So pretty much they're giving you alpha, they're giving you omega 0, and they're giving you theta 0. It then says, at what time after t equals 0 is the reference line at the angular position of theta equals 5 revolutions? The key to this problem is to convert theta from 5 revolutions to radians. How many radians are in 1 revolution? This has got to be known for this class, and your calc class really too. 2 pi. 2 pi. It's a circle. Yeah, don't overwhelm yourself. 2 pi radians is 1 revolution. Write that down if it's not in the back of your head right now. They're going to give problems that have revolutions listed. You need to convert to radians. Let's see. Oh, did you say 10 because I used the word number 5 there?
Yes.
Yeah. So for 5 revolutions, it's 10 pi radians then. 10.
Yeah, that's, oh, okay.
Yeah. So I'm wondering where you got 10 from there. I'm like, how's that randomly 10? Like, he must have thought of something. So this problem asked about 5 revolutions. So Chip thought of 10, but it's 10 pi. 10 pi radians. Okay? It then involves plugging into equations. Okay? It says, again, you're given omega naught, you're given time, you're trying to find when theta is at 5 revolutions. So the equation you would use for that would be this one here. Okay, again, you're told that it starts at no angle or an angle of 0 radians. So this drops off. We're told that the initial angular speed is negative, its velocity is negative 4.6 radians per second. We're looking at it after, let's see. We're looking for the time. It says at what time, so we're going to leave that blank. The angular acceleration is given in the problem as 0.35. And that's in radians per second squared, so I don't have to convert it. And we're told that theta is equal to 5 revolutions. But this we multiply by 2 pi radians for every 1 revolution. Okay? So solve for t. This is a quadratic. This is, all right, this is on page 267.
Should we be in radian mode in our calculation this time?
You absolutely should. Now, is it going to matter right now for this problem? No. But any problem that involves trig, that will matter. But here it will not matter because you're solving generically for t, or solving algebraically for t anyway. Let's see. Don't want to go any further with it. The second part, t equals 32, by the way, sorry. T equals 32 is your answer. It's a quadratic. You could solve it algebraically, graphically, whatever way you want to do it. So if it takes 32 seconds for this to happen, and we look at the context of the problem, it passes that point 5 times in 32 seconds. That's what it means. For this to do 5 revolutions, we're looking at something that literally spins once, spins again. So this point here passes through where it started 5 times in 32 seconds. Does that mean that each revolution took around 6 seconds? Is that what it means? Can we assume that? I'm hinting, obviously. Why can't we assume that? What's the rationale? Why can't we say that each revolution took around 6 seconds? What's the problem, Matt?
It's accelerated.
It's accelerating. Remember, if it were just rotating at a constant omega with no alpha involved, it would just be spinning, right? Who's good at spinning the pencil? Max, it's you, right? Are you the one that spins the pencil on your fingers?
And I feel a lot of pressure.
Like shrug,
So-
can't do it though.
It's really tough to do it. You want to demo it? I know you feel a lot of pressure.
Do it.
Yeah. So when Max sits there and spins it, he's pretty much spinning it. Once it starts spinning, it's kind of coasting at a constant velocity or a constant angular velocity. But he kind of has to push it in the beginning, right? So he's giving it an angular acceleration to start, and then when he stops it, he's giving it an angular deceleration to stop. Okay? So alpha is involved in this problem. The second part of the problem says the following. It says, at what time t does the grindstone momentarily stop? First, how do we know that this is a grindstone moving and spinning? Imagine a disc sander, but you sand the outside and you polish things with a grindstone. How do we know it's going to stop? How do we know it's going to stop? Chris?
Because the angular velocity is negative acceleration.
Yes. If let's go back to linear, right? If I'm walking across the room this way, but there's a wind pushing me this way, eventually that wind is going to cause me, if I have no accelerating force. So let me rephrase this. If I'm sliding across the room at a constant rate, and suddenly the wind pushes back against me, it's eventually going to cause me to stop, right? And then if the wind keeps pushing, what am I going to then do? I'm going to get forced back the way I came. That's what's happening here. This thing is rotating with negative rotations, but the acceleration is positive. So it's doing this, ready? Slower, 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 stop. And then speed up, speed up, speed up, speed up, speed up, speed up, and keep going. So the motion of this object is not only in one rotational direction, it's in two rotational directions. It starts moving in the clockwise direction, and it ends up moving in the counterclockwise direction. And let's prove that. Let's find the time when it stops. If we could find the time that it stops, then we could say to ourselves, by the time it gets to 32 seconds, it is already going in the positive direction. So we've got, for the second part, we know our starting angular velocity is negative 4.6 radians per second. Alpha is positive 0.35 radians per second squared. What equation can I use to figure out when it's going to stop rotating? Again, you need to think linearly and transcribe it in your brain. What equation would you have used in the past if you had initial velocity and you had acceleration and you were trying to find out when the velocity overall equaled 0? What equation would we have used in the past? And then think about how that transcribes to this unit.
Would you use V equals VO plus AT?
Yeah. In the past, we would have used this. Because we have this, we know this is going to be 0, we know the acceleration, and we could solve for time. We would have used that equation in the past for this, but now we're going to use omega equals omega naught plus alpha t. The key is to recognize that omega is 0 if it's going to eventually stop, or momentarily, I should say. It's going to momentarily stop. And then we have to just solve for t. We've got 0 minus negative 4.6 radians per second all over 0.35 radians per second squared. Radians cancel. One of my seconds cancels with seconds, leaving me behind with 1 over seconds, which is really seconds. And this gives me the time period. That's going to be around 13 seconds. So we know that this grindstone stopped at a certain moment and then switched direction to eventually cover 5 full revolutions.
So these are just like essentially kinematics problems.
Yes. The beginning.
Yeah.
We're going to get into more, but for now, and this is where you're going to see these problems will show up multiple choice for sure. The simple ones like these are going to be multiple choice or part of your steps in a longer free response. What we're going to do in 10.4 and 10.5 are the heavier stuff than this. Okay? And 10.3 a little bit too. But 10.1 and 10.2 should be pretty much review, except now with angular stuff instead of rotational, instead of linear. So, I'm going to actually, let me think. Yeah, I'm going to visualize this for you guys on the board, okay? So let's take the eraser. Here's the eraser. This eraser starts with negative angular velocity from last year, negative rotations. Donachek, I was saying, he always made you guys remember. Clockwise, I despise. You guys always did it right? I remember that. I remember saying. That works. So clockwise meant negative. Negative things are despised, right? So when things rotate this way, it's considered negative angular velocity. When they rotate counterclockwise, it's positive. Okay? I also discussed this, but I just didn't use that saying. That saying works, you know? So we've got negative angular velocity to start, negative 4.6. That's the starting angular velocity right here. It's slowing down because the acceleration is this way, slowing down, stopping. Then it starts to do this, and it starts to rotate and rotate and rotate until we get to the point where the starting point is 5 cycles beyond where it was. 5 rotations around that point. Your book is using revolutions and rotations interchangeably. Be careful with that, because revolutions traditionally refer to something that's actually revolving around the central object, whereas rotations are things that are spinning on the axis. So it should really be using the word rotations, but they said revolutions there. So just know that they're using them interchangeably here. Yeah. All right. 10-3. Now what we're going to do is we are going to relate angular and linear parameters. We're going to relate angular and linear parameters. So let's start with this statement. Let's start with S equals theta r. Next, let's take the derivative of both sides with respect to time. So I'm starting with S equals theta r. I'm differentiating both sides. My radius held constant. And as a result, this leads me to an equation. What is d theta dt first? On the right side, what's d theta dt? Omega. What is ds dt? That one's not obvious. What is s? What is s? Good. Along a
Well, S isn't like the arc length.
it's the position along the arc. The literal position along the arc. But S is a linear quantity. S is not rotational. S is a linear quantity. It's that position somewhere physically. It's the length of the arc, right? That's what we used it for in pre-calc. S was the length of the arc intersected by the central angle. So if it's a linear position and we're taking its derivative, what do we then get when we take a derivative of position?
Speed or velocity.
Yeah, speed or velocity. So this turns out that this is the tangential speed. So it's going to be written this way, but write yourself a note that this is the same thing as, remember this equation? It's the same V. It's the tangential speed or velocity. Okay, with this equation, V equals omega r, very useful. Okay, V equals omega r, very, very useful. That is on your formula sheet. That one you don't have to memorize. It is on your formula sheet. So far, so good? Today's a lot of, I don't want to say derivations because we're not deriving much, but more investigation of the different terms based on what we know already. Okay, so that's the first equation. Second part I want to talk about. If an object is spinning in circular motion, we talked earlier in the year by saying that the period it takes is equal to the circumference, right? The circumference over the velocity. And where did that come from? That came from, if you recall, the velocity is the distance traveled over the time period, right? That was from earlier on this year. We said the tangential speed or velocity on on average, is 2 pi r over t. So we switch t and v, and then we substitute for v with its equivalent expression right here. So we're going to take omega r and substitute that in for v over here. Second equation. We know t is also equal to 1 over f. What did f stand for? Frequency. Frequency. Okay, and f was measured, if you remember, in rotations per second. Rotations per second. And it was the inverse of t. Yep. Now, omega is kind of like the inverse of t, but this 2 pi because it's angular velocity here, not linear velocity as before. All right, third one. Let's start again, or let's start this time with this formula now and differentiate this one. If I differentiate this one, I get dv dt equals d omega dt times r dv dt acceleration d omega dt alpha. And this is very interesting, this part here. This is called the tangential acceleration. We're going to put a subscript for a t there. We're going to put a subscript for t. It's not the same thing as centripetal acceleration. This is not centripetal acceleration. Write yourself a note again. This is not centripetal acceleration. Yep.
Is the v up there the tangential velocity?
The v?
In there? Yeah,
Yep.
that's right.
And we don't use t for tangential in the formula, but we'll put the t there if it helps right there, yep?
Okay, t is
Tangential. So let me discuss physically what this would look like. Here. Here's an object moving in circular motion. When any object moves in circular motion, in order to maintain circular motion, there must be some force acting toward the center, and therefore there must be acceleration acting toward the center. The dotted line here is representing the tangential acceleration. So while an object is spinning, if you start to speed it up while it's spinning, you're giving it tangential acceleration. It always has centripetal acceleration. Whenever you spin an object, in order for it to keep spinning, it's got to have centripetal acceleration. But when you speed it up while it's spinning, it means that Vt, take a look, Vt is getting faster. If Vt is getting faster as you spin, there must be some tangential acceleration. Again, if Vt is getting faster, there must be tangential acceleration. How could we figure out the tangential acceleration if we know the angular acceleration times r? Just like how do we find out the tangential speed with the angular speed times r? These formulas are really the same if you look at them, right? This is v, which is velocity, and then angular velocity times r. This is a, which is acceleration, and then angular acceleration times r. They're the same formula. One of them is v, though, and one is acceleration. That's the only real difference here. But the concept is that this is for an object spinning in circular motion that is speeding up now in circular motion. Earlier in the year, when we did circular motion problems, we looked at constant velocity as it was spinning. Vt never changed in those problems. Now VT is changing, causing a tangential acceleration. So we're going to see problems now that have increasing speed instead of a constant speed. Last one for today. Last one. Promise. Centripetal acceleration is really v squared over r. And this is from earlier in the year and from last year. Again, I'm on centripetal now, not tangential. But the v in that equation is the tangential velocity. Right? That equation, that v is really vt. So I can replace vt with its equivalent. And v is equal to r omega. Which makes this r squared omega squared over r. Which makes this r omega squared. So the boxed-in gold equations are your new equations from section 10.3. From section 10.3 involving rotational motion. Rotational motion. My plan for your test and for the next class is to do the following. On Friday, I would like to do some example problems from this section, not the ones in the chapter, because honestly, they're very, very basic, where they would not be problems that you would be tested on an AP exam. They would be a bit too easy. I'd like to do example problems on Friday, and then I'd like to look at 10.4 on Friday. Okay, we're not going to get to 10.5 before the test, so don't worry about it. So 10.1 to 10.3, if you want to read that, you can also get a little bit of head start, read 10.4. You've got a lot of problems from 9.5 to 9.7 to practice. I'll probably give you a quiz on that on Friday, just to give you a heads up. On 9.5 to 9.7. And let's see, we'll finish up with 10.4, and then your test will cover all of Chapter 9 and 10.1 through 10.4. Does that make sense? In case you have an idea of where we're going to go. If we don't get to 10.4 on Friday, I'll drop that. But I think we will. And 10.4, honestly, is just like this was. It's using, I just think we're about to run out. Is it 24 the bell? What time is it?
No, it's 34.
Oh, let's keep going. Let's finish up 10.4. Sorry, guys. I'm thinking we're at the end of the period. That's why I said that. So 10.4 is just like this, but with kinetic energy now. Kinetic energy that we did with translation, now it's rotating. And when an object rotates, it also has kinetic rotational energy. So let's show what that equation is on the next one. So this one here, and I could show a quick derivation of it. Okay, this one, we started with this. We know kinetic energy for a translational object is that. That's what the kinetic energy is. Now, here's the thing, though. If we have a body that's rotating, like this marker is spinning like that, the question becomes where or what particles are physically spinning? And every particle is spinning. That's the thing about this. Every single particle is spinning. And based on where it is, it affects the rotational energy more or less. The further away, the more it affects. The closer, the less it affects it. Now, in this topic, what we're going to do is, we're going to say to ourselves, if we want the total kinetic energy, we can sum together the kinetic energy of all those little particles. So we can say like 1/2 m1, the first particle, and the second particle, and the third, all the way until we get to mn vn. So really, this is just a summation problem of all of these. So the kinetic energy is really just the sum of 1/2 m I v I squared. Now, v from angular velocity, we just wrote a moment ago, is equal to omega r. So we're replacing v with omega r. Replacing v with omega r, which is its equivalent value, omega r. And then actually what we're going to do is this. We're going to recognize that no matter where the particle is, omega is the same. We said that earlier. If this pen, I'm going to spin it, if it spins with 3 revolutions per second as its omega value, doesn't matter where it is. They're all spinning at 3 revolutions per second. So omega can come outside of the summation symbol. So I'm going to put omega squared at the end by itself. And the summation now is just 1/2 mi ri squared. This term is called rotational inertia. Called rotational inertia. It's analogous to what? What is it analogous to? And I have the 1/2 in front, sorry. The 1/2 should be in front here. What is it analogous to? I, based on just the formulas from earlier. So the original kinetic energy, what was there? Mass. I is like mass, but it's like a mass for a rotating body. It's really what's called the mass distribution. Let me give an example so you can see it a bit more fine-tuned. So let's take an object. Here. Okay. So if I have this dowel rod, right? And if I start to rotate it about its central axis like this, it's pretty easy to rotate it. It takes me very little, if no force at all, to rotate this. I'm rotating it about the axis here. How far away are the particles? They're pretty close, right? They're really right next to the rotating axis. But then I'm going to try to rotate it like this. Right? Now the particles are much further from the rotating axis. So in this equation here, mi is going to be a function of the particle itself. R, though, is how far away it is. So a larger I value is something that takes more energy to rotate. So the larger I is, the larger kinetic energy is going to be. Think about it logically. If I try to spin this in the middle, if I physically try to spin this in the middle, it takes me a lot of kinetic energy to do this, as opposed to simply doing this. This takes like no energy at all. So the further away the mass is distributed from the rotating axis, the larger the I value. Again, the further the mass is distributed from the rotating axis, the larger the I value. That's what moment of inertia is. Rotational inertia, moment of inertia. It's really going to be something we're going to get a lot more into detail in section 10.5. And that's going to be probably next Friday right before break. Okay, just so you get an idea of when we're going to cover that. But we're not going to cover 10.5 before the test, where the test is going to be 9.1 through 9.7, and then 10.1 through 10.4. That's all 10.4 is. 10.4 is literally the entire derivation of translational to having many particles, to summing them together, to replacing this v, because this is the velocity, right, when things are rotating, this is vt really, replacing vt with omega r, and then substituting, or then rearranging to put mr squared by itself and omega outside, because omega doesn't change. Omega, whether I'm here or here, is the same omega value. If I'm spinning this at 3 radians per second, this is moving at 3 radians per second, and so is this. The v value in these spots is different, because again, v is equal to omega r. That's why I brought the omega outside of the summation, because it's not a function of position, whereas mass and r are a function of the position with respect to the rotating axis. Let's see if there's an example problem that we could even do here. No. So there's no example problem for this right now, so I'm not too concerned with it. How much did you get into last year in Mr. Donachek's class with torque? Did you guys talk about torque at all? Yeah? Good. Okay, because we're going to talk about torque when we get back. We did a good amount in my class as well. And we're going to talk about what's called rotational equilibrium, where like there are two torques and they balance an object. And we'll see if we have the fulcrum and stuff. We're going to talk about that one after this next test. Okay? Any questions, guys, for the test as to what's going to be on? I mean, we have Friday still, and Friday we're going to really just look at problems from 10.1 through 10.4. Before Friday, you should be working on 9.5 to 9.7. homework problems. I sent you all the free response and multiple choice samples I have. You're not going to physically be able to do them all, but try to look at them, meaning you don't have time to do them all, but try to look at a couple if you want to in there. And then Friday we'll review 10-1 and 10-4.
The homework that was due today was that graded based on accuracy?
The ed puzzle?
Yeah.
I think I pushed that to do tomorrow, actually.
Okay.
It's
Yeah.
due at midnight tonight.
Oh, is that
Or
right?
11:59.
Oh, because it locks you out online,
Yeah.
doesn't it? Crap, okay, I gotta look at that. Maybe I can change it to tomorrow.
It-
But 11:59 tonight, pretty much tomorrow. Don't do it tomorrow during school, is what I'm getting.
It takes.
It probably takes, what, 10-15
It
minutes?
takes 10 minutes,
Yeah. So you're just watching a video. I'm thinking about doing this just as a review for upcoming lessons. The channel that the guy uses called Flippin' Physics is a great channel. It's the one I recommended earlier this year. So if you're a proactive person over spring break, honestly, I would watch all of his Flippin' Physics videos on stuff that we've covered already. Just a review to get a little bit of a sense of like where are we headed with this. And then as the year progresses, I might assign a couple more ed puzzles. I might do that next year more, and I'm just kind of trying it out with you guys this year. That's the reason
He's
for it.
quite enthusiastic.
The videos are incredible.
Yeah, they're really fun.
He like does so much video editing. It's him, you know, right?
Yeah.
He plays the students also in the video. So watch it and see what I mean.
Yeah,
I give the guy a ton of
He's
credit.
very
and
bridge.
Bridge. It's like videos that you would create, but like even more advanced. I would definitely look at it.